Greetings and welcome to lesson 4.6 Poisson distribution. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. For the Poisson experiment, there are two main characteristics that differ from any of the other distributions. The first is the experiment can consist of counting number of times the event occurs given a specific interval. That interval could be based on a fixed time or space, as in area or volume. For example, if a book editor might be interested in the number of words spelled incorrectly in a particular book, it might be on average there are 5 words misspelled within 100 pages. The interval would be 100 pages. Secondly, the number of occurrence in one trial is independent of the number of occurrence in other intervals. This random variable is the number of occurrences in the interval of interest. So maybe our interval is next time 200 pages. So the number of occurrences is independent whether it was in the first 100 pages of the book or the last 200 pages of the book. Those two intervals are independent. The number of occurrences are independent. The other fact is the Poisson probability distribution is closely related and is approximate to the binomial distribution if your success is small, like 0.001, and the number of trials is large, such as 1,000. To use the Poisson distribution, we're going to need 3 things. 1, we're going to have to figure out the interval of interest. 2, we're going to have to figure out the average number of times something happens within that interval. And 3, what values does x take on? Using those 3 things, we can figure out the Poisson distribution for a particular probability. So let's gather the information out of this very short problem. You notice the news reporter says, on average 2 times per broadcast. What is the probability that the news reporter says, more than 2 times per broadcast? This is a Poisson problem because you're interested in knowing the number of times the news reporter says, during a particular period of time. What is the interval of interest? It is 1 broadcast. What is the average number of times the news reporter says, during this 1 broadcast? It says on average 2 times, so 2. What values does x take on? X can take on 0, 1, 2, 3, and continue. The probability in question is P what? We want to know is the probability that the news reporter says more than 2. So the probability that x is greater than 2. And we didn't do any math yet. All we did is pull out the information to prepare us to use the math for the Poisson distribution. I want to take a little bit of a side tact here talking about Poisson distribution. Our textbook, I don't want to say has a unique way of describing the function of the distribution, but I haven't seen it written like this very much in other textbooks and in online resources. And because of that, I just wanted to show you the difference of how our book uses some notation and what other resources use. Our textbook for the notation of the actual distribution is x tilde p mu, where mu is our mean of our distribution. Other resources uses another Greek letter called lambda for the mean. So x tilde p lambda. I don't want to say that these 2 things are different. They are the same thing. Mu and lambda are the same thing, but I want to show you how it looks different, although the meaning is the same. For our textbook, the mean is calculated mu equals n times p. Generally, the mean will actually be given to you, but if you do have to calculate it, it's n times p. For other resources, the only difference is they use lambda instead of mu, so lambda equals np for the mean. Standard deviation is sigma equals the square root of mu. That's for our textbook. For other resources, you might see it as sigma equals the square root of lambda. And because we're using lambda for other resources and mu for our textbook, yes, the formula for the Poisson distribution looks slightly different. Our textbook writes it like this. The probability of x equals e to the negative mu times mu to the x divided by x factorial. When you look at other resources, they put the lambda in front and they write it as one fraction. So lambda to the x, e to the negative lambda, all divided by x factorial. Now, generally, we will not use this calculation. We'll use our calculator to do it, or we'll use an online resource. But because you might be using an online resource, I did want to show you that they use a different symbol for the mean. They use lambda out there in the world versus our textbook uses mu. One is not wrong, one is not right. It's just different notation. Let's use Poisson, and I'll get to the formula in just a moment. We do have a new variable, a new letter that we're going to use, and I'll explain that once we get to the equation itself. Here's the problem. The average number of loaves of bread put on the shelf at the bakery in a half an hour is 12. Of the interest of the number of loaves put on the shelf is 5 minutes. So we want to know what's the average in 5 minutes of the amount of bread that we put on the shelf. What's the probability that the number of loaves selected randomly put on the shelves in 5 minutes is 3? The first thing is our average is based on a half an hour, and we only need 5 minutes of those. So if the average number of loaves put on the shelf in 30 minutes is 12, then the average number of loaves put on 5 minutes, 5 divided by 30 times the 12 is 2 loaves of bread. So that's our general average. The probability asks us to find P when x equals 3. So the amount of loaves we're looking for, 3 within the 5 minutes on the average is normally 2. Here's our formula. The probability of x equals lambda. It's just a new Greek letter. I'll explain it in just a second. Lambda to the x times e to the negative lambda all over x factorial. Lambda is our average of the interval. You can think of it as mu. It is an average, but it's the average of the interval. E is a value you may or may not have worked with before, but it is an actual number like pi. E is 2.71828. And in this case, our x value is 3. Plugging in those values into our equation, we get P of the 3 we're looking for will equal 2 cubed e to the negative 2 all over 3 factorial. Most calculators can handle this. Most calculators have factorial. Calculators have exponents, and most calculators have an E button. So you could pretty much just throw it into the calculator and you get 0.1804, meaning that's the probability of having 3 loaves of bread within 5 minutes, about 18% of the time. This is the problem that we're going to work through using the TI-84. Now, during the video, you will be able to see the problem, but we're going to be looking for the Poisson possibility that an email user receives exactly 160 emails, at most 160 emails, and more than 200 emails. We have 2 different functions in the TI-84 Plus for the Poisson distribution. Those are the Poisson PDF and the Poisson CDF. It depends on what your problem is, which one you're going to use. If you're going to find exactly a particular amount, like x equals 2, then you're going to use PDF. If you need less than or equal to a particular value, then you're going to use CDF. And if you need greater than or equal to, then you will use 1 minus the CDF function. Here's an example. According to Baden, an email management company, an email user gets on average 147 emails per day. We're going to figure out what's the probability that the email user receives exactly 160 emails a day. So we're going to go to our Poisson, so second distribution, and we're going to go up instead of down because it's near the bottom. Poisson PDF because we're looking for exactly 160. So let's go to C. Enter. Our lambda is our normal average for our time interval. In this case, on average, there are 147 emails per day. So 147. Our x value we're looking for is 160. What's the probability that an email user will get 160 given that the normal average is 147? And it looks like it's about 0.180 is the probability. In other words, 1.8% of the time they will receive 160 emails. Let's figure out at most 160. So they could get 0, 1, 2, 3, 4, all the way up to 160. So we're going to use CDF this time. Second vars. And I'm going to use CDF for the Poisson. Enter. Our average is still 147. And our x value is still 160, I think is what I said. We want to know if they will receive at most 160. This time is 0.8666. In other words, 86% of the time, they will receive up to 160 emails. 86% of the time. Let's see if a customer will, what's the probability that they'll receive over 200? Now, because I want to know if they'll receive over 200, it's going to be 1 minus the Poisson CDF. Second vars Poisson CDF. Our average is still 147, but we want to know what's the likelihood that they'll get over 200 emails. And it is an incredible small amount. It is 0.00001 is the probability that they would receive over 200 emails. That's it for Poisson distribution. If you are looking for an exact amount, then you will use Poisson PDF. If you need less than or equal, you'll use Poisson CDF. And if you need greater than or equal or more than, then you'll use 1 minus the Poisson CDF. So until next time, be safe.
The three distributions that we've gone over: binomial, geometric, and Poisson. Binomial distribution needs to meet three conditions. 1, there are fixed number of trials. 2, only 2 possible outcomes, success and failure. 3, the trials are independent and repeated using identical conditions. Geometric distribution has to meet the 2 conditions of binomial. There are only 2 possible outcomes. The trials are independent and repeatable using identical conditions, but they are all failures except the very last one, which is a success, and then you stop. Second condition, in theory, number of trials could go on forever because you're just looking for your first success. There must be at least 1 trial. So if you don't do it, it's not a geometric distribution. But as soon as you start, you must continue until you have success, then it's a geometric distribution. Probability of success and probability of failure do not change from trial to trial. Those are the conditions for a geometric distribution. Poisson distribution has two criteria. The probability that the event occurs in a given interval is the same for all intervals. And the event occurs with a known mean, and it's independent of time since the last event. So if we're dealing with specific intervals of time or space, then it's Poisson distribution. There are other distributions out there. We're just not going to focus on them this go round.
You've reached the end of this lesson.